Welcome to the Introduction to Organic Chemistry Simulation. Today you will learn the basics of organic chemistry and how this is connected with carbon, an essential element for all life. You will understand how organic compounds can be represented and perform simple experiments to identify some functional groups. Let's go check out what's wrong with Simon.
Hey, thanks for coming by. This toothache is killing me. I hope the pills my friend gave me relieve the pain soon. She said they contain salicylic acid, and that it's an organic compound with good anti-inflammatory properties. However, I don't understand why she said it's organic. It doesn't grow in the fields like carrots or cotton. I thought you could only find organic compounds in organic food or fabric. I was thinking, since you're into chemistry, why don't you go to the lab to find out what these organic compounds are? Also, it would be nice if you can confirm that these pills are really salicylic acid. I don't want to repeat that experience with the alchemist.
I'm sure you also had toothache and remember that it's not a fun experience. Will you be able to understand the basic chemistry of the organic compound Simon has been given, and confirm that he doesn't need to worry about these pills? Pick up a lab coat from one of the lockers to get started. Interact with the lab pad for more info. Click on the lab pad for more information. What makes organic chemistry so interesting? Have a look at the screen on the wall to your right. What do these three images have in common? Exactly. The backbone common to DNA, sugar, and coal is carbon. DNA is present in all living cells, and both sugar and coal are produced from living organisms too. Did you know that you are actually 18% carbon? Because carbon is the backbone element for life. The study of carbon-hydrogen-based compounds is called organic chemistry. We'll start by getting you up to speed with basic organic chemistry before we look further into the mission from Simon. Are you ready for a fascinating journey into organic chemistry? Then let's move to the hollow table to the right side of the lab. Go to hollow table 2. Here you can see a methane molecule, one of the simplest organic compounds. In the 3D models, black represents carbon and white represents hydrogen. But why are carbon and hydrogen bound in the way they are? Let's look into the bonds of carbon in this atomic animation. The carbon atom has 6 electrons. These electrons have the following orbital configuration: 1s2, 2s2, 2p2. This means that there are 2 electrons in the inner 1s subshell, 2 electrons in the 2s subshell, and 2 electrons in the 2p subshell. The 2 electrons in the 1s subshell are not of interest in organic chemistry, so we'll leave them for now. We are now looking at carbon's valence electrons, which are those that are used for forming bonds. Let's check out how they are arranged. 2 electrons are orbiting in the 2s orbital, and 1 electron is orbiting in each of the 2px and 2py orbitals. As you can see, the 2pc orbital is currently empty. Carbon normally forms 4 bonds, but here, only the 2 2p electrons are unpaired and available for a chemical bond. How can that be? We can get 4 unpaired electrons through excitation of one of the 2s electrons into the unoccupied 2pz orbital. Carbon is now almost ready for forming bonds. Carbon bonds depend on the type of hybridization that takes place in the electron orbitals. Hybridization is a process where the orbitals mix to form hybrid orbitals. Let's see the different types of hybridization, starting with the most simple one, the sp3 hybridization. In order to form 4 bonds with other atoms, the 2s, 2px, 2py, and 2pz mix to form 4 equal orbitals, called sp3. This is the process of hybridization. The sp3 orbitals form the 4 corners of a pyramid with triangular sides, a so-called regular tetrahedron. The angle formed between the orbitals is 109.5 degrees. With the sp3 orbitals, each occupied with a single electron, carbon can form 4 equivalent single bonds with e.g., hydrogen. These are called sigma bonds. The angle between the orbitals will determine the angles between the chemical bonds the carbon atom will make. So when forming sp3 orbitals, the angle of the bonds will be 109.5 degrees. A carbon atom can also bind to another carbon atom using a sigma bond. The rest of the sp3 orbitals can then form more sigma bonds with other compounds. For instance, with hydrogen to form ethane, as shown here. Let's have a look at another type of carbon hybridization, sp2. With sp2 hybridization, the 2s, 2px, and 2py mix to form 3 equal orbitals. The pz orbital will stay intact. The angle between the sp2 orbitals is 120 degrees. The sp2 hybridization is used when carbon forms double bonds, e.g., with another carbon. One sp2 orbital is used for a sigma bond. The pz orbital is used to form what's called a pi-pi bond. Even though the pi bond locks in 2 places, it only corresponds to a single bond. The remaining sp2 orbitals can bind with sigma bonds to other atoms, such as carbon, oxygen, or hydrogen. The bond angle will as before be determined by the angle between the orbitals, and will therefore be 120 degrees. If there are only bonds formed with hydrogen atoms, an ethene molecule is formed. Let's have a look at the sp hybridization, the last one for now. In sp hybridization, only the 2s and 2px mix to form 2 equal orbitals. 2py and 2pz stay intact. The angle between the sp orbitals is 180 degrees. The sp hybridization is used when carbon forms triple bonds, e.g. with another carbon. As with sp2, a sigma bond is formed using one of the sp orbitals. 2 pi bonds are formed with py and pz. The remaining sp orbitals can form sigma bonds to other atoms. The angle between the 2 sigma bonds will be 180 degrees. If only hydrogen atoms are bonded to, then an ethyne molecule is formed. That's it for now. Let's go back to the lab for a little quiz to see if you've got this. Let's see if you understood the essentials of the animation. What is the valence value of carbon? Yes, the outer shell of the carbon atom has 4 electrons, so this is its valence value. When carbon binds to 4 other distinct atoms, what is the angle of the carbon bonds? Good job. When carbon forms bonds to 4 distinct atoms, it has 4 sp3 hybrid orbitals that are organized forming a regular tetrahedron structure. This means that the angle between each bond is 109.5 degrees. Click the molecules on the hollow table to check them out. Interact with. Besides methane, you now see 2 more molecules on the hollow table, formaldehyde and carbon dioxide. Note that the red atom represents oxygen. Can you spot the correct statement for methane, formaldehyde, and carbon dioxide? You nailed it. They all have different bond angles. Bond angles are very important, as you now know, a carbon with only single bond. Click on the hollow table to go back to the center of the room. Go to hollow table 1. Your mission here is to build the proposed molecules by adding the hydrogen atoms at the correct angle. New hydrogens can be picked up from the left on the hollow table. You can discard excess hydrogens in the trash bin. The molecule can be rotated by clicking the white arrows on either side of it. This way you can get a good view of all the suggested hydrogen positions. Let's see if you can identify the correct configuration. Place all hydrogens in ethane at the correct angles. Interact with the lab pad for hints. Good job. Can you do the same for propane? Awesome. Can you do it for propane as well? Well done. It looks like you now know the bond angle of each atom depending on the type of compound. I'm sure you've also noticed that for each extra bond added between 2 carbons there will be 2 fewer hydrogen atoms in the compound. Besides being found in living organisms and their fossils, organic compounds can also be synthesized in the lab. Let me show you a few more examples of where we use them. Click the hollow table to go to the screen by the entrance to have a look at some organic. These are some of the carbon-based materials that we use every day. They are used as a source of energy in the food we eat, as fuel for our cars, and to make the water bottles we buy in the supermarket. But these are just a few examples. There are many, many more, and the organic compounds they are made of have many exciting features. Let's check out some important aspects of them. In this picture you can see the 2D structure of 2 hydrocarbons. Can you spot the difference between them? Well spotted. When representing 2D structures of organic compounds, lines connecting atoms represent bonds. And compound B has a carbon-carbon double bond, which also means it has fewer hydrogens. Note that in 2D structural formulas like these, we can choose not to take the three-dimensional arrangement into consideration. Saturated hydrocarbons, also called alkanes, have only single bonds connecting the carbon atoms, while unsaturated ones have double and or triple carbon bonds in their structure. According to the International Union of Pure and Applied Chemistry, simpler hydrocarbons are named by considering two factors. First, the number of carbons. We use a prefix according to the number of carbons in the molecule. You will find a useful table in the theory section. Let's see if you've got this. What is the name of this compound? Well done. This is the structure of hexane. It's an alkane with 6 carbon atoms. Hexane is one of the major constituents of gasoline. The second basic factor to name a hydrocarbon is based on the types of carbon bonds present in the molecule. We use a specific ending depending on the type of hydrocarbon. Now have a look at these hydrocarbons. Which compound is not present? Right again. From left to right, the molecules are ethene, but2-ene, methane, and ethyne. Now that you know how to name simple hydrocarbons, let's go use this in a little exercise. Go to Hollow Table 2. Which compound is being shown on the hollow table right now? Exactly, but1-ene is so named because it has 4 atoms of carbon. The prefix used is therefore but. Since it has a double bond, the suffix used is ene. Finally, the number represents the first carbon involved in the double or triple bond. When needed, each carbon can always be assigned a specific number in the structure. In this minigame, we'll see if you can relate 2D structures to the right 3D configuration. A 2D image of a hydrocarbon will appear on the screen in front of you. By clicking the ABC buttons on the hollow table, you will see 3 different suggested 3D structures for the shown hydrocarbon. Click the OK button when you think you've selected the correct 3D structure. Are you ready for this challenge? Awesome. You're right, this is propane. It has 3 atoms of carbon that are using just single bonds. Note that all bond angles are the same, specifically 109.5 degrees. Round 2. Click the OK button when you think the correct 3D structure is showing. Nice. You're correct. This is Hex3-ene. It has 6 atoms of carbon and 1 double bond connecting carbon 3 and 4, which forms a 120 degrees angle, while the rest of them have 109.5 degrees bond angles. You're doing a great job. What would you like to do now? Besides identifying simple hydrocarbons by their structural or 3D formula, there are chemical tests that help you confirm or discard the type of hydrocarbon you are working with. One of the simplest tests is called the Bromine Test. It reveals whether a solution contains unsaturated organic compounds, as the bromine reacts with the double and divided pure triple bonds. Do you want to help me with an issue where we'll use the Bromine Test? Alright, click on the hollow table to go to the wall screen next to the lab entrance. Before we go to work on Simon's issue, you need to know a bit more about organic compounds. There is virtually an infinite amount of them. This is possible due to the existence of isomers and functional groups. Isomers are compounds with the same formula, but with a different arrangement. Go to Hollow Table 2 to learn the basics of functional groups. What is a functional group then? Functional groups provide the reactivity to the organic compounds, and their position also determines how the compound is named. Here on the hollow table, you can again see formaldehyde, which contains double bonded oxygen. That oxygen is a functional group, and when placed this way, the whole compound is called an aldehyde. There are a lot of different functional groups, and some of them contain atoms other than hydrogen and oxygen, such as nitrogen, phosphorus, and sulfur. Do you remember the definition of an organic compound? From this image, which compound would you say is not considered an organic compound? You're absolutely right. Even though calcium carbonate contains carbon, it is considered to be an inorganic compound, as it does not contain any carbon-hydrogen bonds. Be aware that a carbon atom can actually change from being part of an organic compound to being part of an inorganic one, and the other way around. As you can see, we sometimes don't write the C for carbon and H for hydrogens attached to these carbon atoms. These are called skeletal formulas. The carbon atoms are implied at the corners of the structure. It might look a bit confusing in the beginning, but it is actually really helpful for quickly identifying the important aspects of the molecule. Now, let's get to work on your mission from Simon and see what we can learn about salicylic acid. Click on the hollow table to go back to the center of the room. Find a glove box and click on it. Put on the safety goggles. Return to the screen on the wall next to the entrance. Salicylic acid is also called 2-hydroxybenzoic acid. It's a compound obtained from the bark of the white willow and wintergreen leaves, but it can also be synthesized in a lab. This is the structural formula of salicylic acid. You can see 3 clear functional groups, a hydroxy group in purple, an aromatic group in blue, and a carboxyl group in green. The hydroxy group can be part of different functional groups. When bonded to an aromatic ring as in salicylic acid, the functional group is called phenol. In fume hood 2 there is a solution of pure salicylic acid in water, prepared using the pills you brought. You will also find water and hexane, which we will use as negative controls. The positive controls for the respective tests will be ethanol, phenol, and acetic acid. You can have a look at the media tab to see their 2D structure at any time, and check out what it means to have controls in an experiment in the theory pages. Click on the screen to go to fume hood 2. As an extra challenge for you, I did not label the 6 test solutions, so you don't know what's in each beaker. Let's see if you can find the salicylic acid solution and confirm that the pills actually contain the functional groups of this organic compound. You will first test for a hydroxy group using the steric ammonium nitrate test. According to what you know about the structure of salicylic acid, what should happen to that solution after performing this test? Alright, we'll find out if your hypothesis is correct after you've done the experiments. Add each solution from the beakers to a different test tube. Click on the lab pad for more information. Let me help you with the remaining tubes. Add steric ammonium nitrate to all the tubes. Let me help you with the remaining tubes again. Vortex the tubes and observe the results. Click on the lab pad for more information. Good work. Which compounds seem to have either an alcohol or phenol functional group? Exactly. Those beakers seem to contain solutions of compounds with an alcohol or phenolic functional group. Alright, now you have narrowed down your options. Let's do a second test to find our sneaky salicylic acid. Go to fume hood 3 on your left. In the second test, you will look for signs of a carboxylic acid group. The addition of sodium bicarbonate to a solution containing an acidic compound results in the formation of some brisk effervescence, as the bicarbonate is converted to water and gaseous carbon dioxide. I've already transferred some of the test solutions for you into 6 fresh tubes, so you can get to work. What should happen to the salicylic acid solution when performing this test? Okay, also we'll see if your hypothesis is correct after all the experiments. Add sodium bicarbonate to a tube. Nice. Now add sodium bicarbonate to the remaining tubes and observe if anything happens. Alright, which compounds do you think contain a carboxylic acid group based on this test? Well done. You can see brisk effervescence in those tubes, meaning that they contain a carboxylic group. As before, you can see an overview of the results in the Media tab. Put the spatula back in the beaker. Click the fume hood to go back to the screen on the wall and have a look at the final result. Now that you have performed the experiments, tell me, where was the salicylic acid hiding? You can check the Media tab to have a look at the structures of all 6 compounds again. Interact with the lab pad to answer the question. You are a chemistry champion. Compound A was the salicylic acid, indeed. It's the only compound that gave positive results in both tests, which matches with the presence of phenolic and carboxylic acid functional groups at the same time. So now you can confirm to Simon that he doesn't need to worry. These pills are safe. Now, let's check how good your predictions were. Your first hypothesis wasn't correct. Since salicylic acid has a phenol group, the addition of ceric ammonium nitrate makes the solution turns to a dark red color. But hey, you got the other one right. Not bad. You've done a great job. Let me ask you one last question. Looking at the results, can you determine which one is hexane? Brilliant. That's the mindset of a true scientist. You don't have enough data to conclude which compound is hexane. Therefore, you would need to perform more experiments to determine which beaker contains hexane. However, you might have noticed that compound F formed 2 layers in the ceric ammonium nitrate test. This gives us a clue that this might be hexane, as this compound can't be mixed with the aqueous solution of ceric ammonium acetate. I hope you come back another day to complete your training in advanced organic chemistry. We're almost through the simulation now. As a little present, have a look at the 3D structure of salicylic acid on Hollow Table 1. Go to Hollow Table 1. You know, the pills you brought were just aspirin. Aspirin is also called acetylsalicylic acid, and it's broken down into salicylic acid in your body. For the tests in the lab, I did this conversion for you. Simon can trust his friend. She gave him a very common and effective treatment for simple pains and inflammatory processes. Let's go see how he's doing.
I feel much better now. Thanks for helping me understand my friend's recommendation. Because of your explanations, I now can't stop identifying organic compounds.
Today we are using charcoal to light up the barbecue. The meat and vegetables we'll eat contain proteins and carbohydrates. We have plastic bottles for the soda. I wear a nylon shirt. And if I feel bad again, I will take some more acetylsalicylic acid pills. Chemistry is everywhere. I can't wait to learn more about organic chemistry. It's so amazing.
Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now. Press exit to close the simulation. This will open a survey. Please take 1 minute to provide your feedback. It will help us to improve Labster. I gained relevant knowledge by using the simulation. I found the simulation motivating. I feel more confident about my lab skills after the simulation. I feel that I can apply what I have learned in the simulation to real-world cases. In general, I was pleased with the simulation. Thank you for your feedback. Please exit the lab by pressing escape. See you in another lab.